Okay, so hello everybody. Today is September 1st, and we're talking about functions today. We're going to talk about just describing some functions, some function families, and then a little bit about function notation. So first, on to describing graphs. One of the first things you can kind of look at is whether a graph or a relationship is continuous. Continuous means it'll be connected and all the values make sense here. So that if I'm going to buy gas, I could buy 1 gallon, 2 gallons, or 3 gallons, but I could also buy like 1.5 gallons or 2.75 gallons, so that any of those points are possible. Sometimes they're discrete and the numbers in between don't make sense. They're dots. So discrete looks like dots. And here, if I'm buying a shirt, the one shirt costs $2, or one shirt costs $15 to $30. And it's not like I can really, it makes sense to buy 1.5 shirts. So they're discrete, they're separated, and they're dots. The next is linear or nonlinear. Linear relationships increase at a constant rate, like that shirt. It increases $15 for every shirt. The graph, that's the y. Like over here, for every 1x, the y is increasing 2. We say that's linear. Otherwise, we have nonlinear relationships, and I get all kinds of different curvy things. Asymptotes. This is a pretty complicated idea, but basically it's when a line gets really a curve gets really close to a line but never quite touches. So like in this first one here, I see that there's a horizontal asymptote at y equals 0. This curve is getting really, really close to that. Over here, there is a horizontal at y equals 3 and a vertical at x equals 2. And I've got these two curves getting close on either side. Intercepts are where graphs cross the x or y axis. Where the relationships have either a 0 value or a 0 x value or a 0 y value. So like in this first graph, I can see I have a y-intercept there at -2, 0. That's the x-intercept, pardon me. And then over here, I have a y-intercept where it crosses the y-axis at 0, 4. Here's a y-intercept. It crosses the y-axis at the point 0, 2. So x is 0, but here I've got that y. Over here, I've got a y-intercept at the point 0, 5. I can also look to whether the relationship is increasing or decreasing. And I really want to make sure it's kind of strictly increasing, like it's going up everywhere, like those two, or it's going down everywhere, strictly decreasing. It's like this one's going down, and there's a linear relationship that's going down. If it does both, it's neither increasing or decreasing. So some families of functions, linear functions, it's always, so like right here is a linear function. Direct variation is a line that goes through the origin, 0, 0. Inverse variation is kind of, it's this curvy relationship. And actually, if I multiply my two variables, my x and y, I get a constant. The hot tub lab, where I wanted an area of 36. So if I multiplied the length and width, I always got 36. So points that worked were like 1 and 36, and 2 and 18, 3 and 12, 4 and 9, 6 and 6. And that's I get an inverse variation. Exponential function is when the function is increasing by a multiplied value. So like a flu epidemic where it was multiplying by 3 every time. So here's the hot tub example where I can see that these are all these points, the x and y, they are a multiple of, they multiply to 36. And if I was going to describe this, it is a discrete because they were using whole tiles. It's nonlinear because it's curvy. It's decreasing everywhere. And it has the horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0, and its inverse variation. The flu epidemic, it was multiplying, it started with 2 people, and then 6, and then 18, and then 54 is multiplying by 3. This is a discrete because it's dots. It is nonlinear because it's curvy. It's increasing because it's only going up. And it has a horizontal asymptote at y equals 0. And an x and a y-intercept at 0, 2. It's an example of an exponential function. Signing on a dotted line where people made a signature and then timed how long it took them. This is a discrete because they waited for a whole signature. It's linear because it's increasing. It's linear, so because it's in a line, and it's increasing because it's going up as the number of signatures passed on, the time went on. It had an x-intercept and a y-intercept at 0, 0. It's an example of a linear function. A little bit about function notation. A function is a relationship between two values, an input and an output, and each input has exactly one output. So if here I put in x, the machine does its thing, and then the output is 9. So a little bit about this notation. We often use the letter f. This right here, it's not f times x, it's f of x. And here it's saying equals x minus 2 squared. This over here indicates the operations done to the inputs to get the outputs. So if I look at f of 5, meaning, okay, 5 is getting input, and I'm gonna substitute the 5 in for x. And then I'm gonna start doing it. First I subtract 2 because it's inside the parentheses, I get 3. Next I'm gonna square that value and I get f of 5 equals 9. So the input is x, so 5 is the input x and 9 is the output y. Let's look at one more example. F of x equals square root of x plus 3. So basically I'm going to have my inputs x and I'm going to add 3 and then square root. So let's find f of 6. So here f of 6, I substitute 6 in for x. First I'm going to add 3 and I get f of 6 equals the square root of 9. So then I'll square root that and I get f of 6 equals 3. So for the input 6, the output is 3. So when x equals 6, y equals 3. I could graph that, I could put it in a table. Just a quick definition about some variables. This is just language. The independent variable, this is the input, and we usually use the variable x. It's the one that's kind of doesn't depend on another one. Dependent variable, this is the output. We usually use the variable y. Its value does depend on that of another. So some examples, if I'm looking at patterns, the pattern number is x, the independent variable, and that's going to cause a change in the number of tiles, or the y, the dependent variable. The number of signatures, x, that's my independent. That caused a change in the time it takes. That's y, my dependent variable. In the flu epidemic, the number of days, x, was my independent. The number of people infected is my y dependent. All right, everybody, hope you all have a wonderful day, and I will see you all soon.